Welcome back. We continue with the final part of our program, last two presentations, and we'll proceed with Nicholas Roy, who's Bisplinghoff professor in the Department of Aeronautics and Astronautics, and he is Director of Quest Systems Engineering at MIT's Quest for Intelligence. So, Nick, take it away.
Thank you very much. So it's great to be here. I'm going to talk to you about an exciting new initiative at MIT. Started only a couple of years ago. And then I'm going to talk a little bit about some of the specific research that's happening inside the Quest as well as inside my own research group. So what is the Quest? It's a quest for understanding intelligence, how brains produce it, and how it could be replicated in artificial intelligence. So AI, machine learning, is having a tremendous impact in the world all over. But there are more things to be done, and there's more research directions that we can pursue. But AI and understanding of intelligence, not just artificial intelligence, but understanding artificial and natural intelligence, is a real challenge right now. As a society, as a humanity has addressed these big challenges in the past, whether it's understanding the basis of nature through physics, whether it's understanding how biological systems replicate. I mean, these are big challenges that we have taken on over the centuries. And the hypothesis of the Quest is that understanding intelligence is the next big one. We have some ideas about how intelligent systems work. We have some demonstrations of artificial intelligence systems doing useful things. Most of you, I assume everybody here has a smartphone, and it's doing things like translation and image recognition on your smartphone. So we have existence proofs, both from the natural world and the artificial world, about what intelligence might look like. But we don't really have a unified theory that draws from the natural intelligence and is tested in the artificial intelligence. And so really what the Quest is, as a research enterprise, is developing new scientific theory, hypotheses about the mechanisms for natural intelligence, which we think will lead to a new state-of-the-art in artificial intelligence. And so that's really what the Quest is about, is really aiming to create a new field, which is the science and the engineering of intelligence. Really two sides of the same coin, and really one unified discipline that we think will lead to a better world. And well, let me explain what we might get for this. What are the payoffs if we actually start a new discipline of intelligence? So one is we might get the next generation of AI, and I'll explain in a minute what we mean by the next generation of AI. But that's really how the natural intelligence can inform artificial intelligence. If we really lean into this effort in terms of science and engineering, how does the engineering also help? Well, it gives us perhaps a better understanding of natural intelligence. It may allow us to transform education, give us a better understanding how people learn. It might give us better understandings of biological systems that allow us to do better diagnosis of brain disorders. And it might just, hopefully, in the fullness of time, it will give a better understanding of ourselves. So where are the fields right now? What we see is that artificial intelligence, as I said earlier, and machine learning are ubiquitous in society, that it affects our lives in ways that we don't even necessarily understand. But there are significant limitations with current approaches, and many of you may be seeing these limitations already. So on the science side, there's tremendous research going on in understanding how the brain works and how natural intelligence happens. But we don't really have the ability to replicate even some of the basic capabilities of a 2-year-old or a 3-year-old in silicon. So our scientific theories are not allowing us to actually advance the state-of-the-art in engineered systems. The engineered systems are only partially guided by natural intelligence, and they have limitations in terms of they're very data intensive. If you've worked in modern AI machine learning, you know how expensive data can be and how much is required. They're also very energy intensive. So a study done at the University of Massachusetts Amherst about 4 years ago identified that training one modern machine learning system, what is typically referred to as a deep network or a neural network, has a carbon footprint of driving an internal combustion engine car for a single year. So that's unacceptable for obvious reasons related to climate change. But also as an engineer, it's unacceptable because we know that natural intelligence is much more energy efficient. The power required to run the human brain is a little hard to compute, and the literature is not clear on this number, but it's somewhere between 25 and 60 watts. So less than one of our old incandescent light bulbs is the energy consumption. So that's a problem. How do we get the energy efficiency of natural intelligence in silicon? And the other issue is that there's a lot of development going on in labs like CSAIL, in departments like Brain and Cognitive Sciences to understand these phenomena and build new systems, but they're not necessarily well connected to applications. So part of the charge to the quest and part of the vision of the quest is that the best way to actually develop new theories, develop new systems, is in the context of real applications. Rather than bolting on our theories onto applications, let's actually develop the theories and the models in the context of applications. So what's hard about bringing science and engineering together in this way? Well, let's use an example that we actually do know how to understand in a model, which is your smartphone. Now, I think that we all understand that the smartphones contain a large number of components. What the fundamental building block of a smartphone or any electronic device is the transistor. And we understand transistors extremely well. The building block of brains and natural intelligence is the neuron. And we understand neurons extremely well. But it's hard to imagine getting an understanding of the complexity and the utility and the performance of a smartphone like this by examining how the transistors are connected and work together. We know that there's a tremendous amount of structure inside those phones. The transistors form logical circuits. The circuits form integrated chips. They form a system motherboard. There's software running on top in terms of an operating system and user applications, et cetera. How can we get the same level of structured understanding of natural intelligence if we're only examining neurons and synapses? So part of what is required and part of what the Quest is investing in is a better understanding of the internal structure and the organization. This is not to in any way belittle or throw shade on what our neuroscientists have done over the last couple of hundred years in terms of understanding the brain and the nervous system, but there is a need for a more structured and engineered approach. Building these kinds of modular structures is exactly what engineers do. It's how we put things together and build new things. And by bringing science and engineering together in pursuit of intelligence, hopefully we can get the same kind of engineered understanding that allows us to separate concerns, allows us to reason at different levels of abstraction, and so on. Why do we think this is possible? Well, there's examples of past successes. So many of you may recognize our esteemed president, President Reif. How did you do that? Well, we actually have a pretty good understanding now of some parts of the visual pathway in terms of how the photons enter your eye, they're processed by the retina, signal travels through way stations of the brain to arrive at the visual cortex, and so on. And what's interesting is that we also have computer systems now that can do the same kind of image recognition of President Reif. And what's interesting is that a lot of early computer vision was not necessarily well informed by natural intelligence. And computer vision researchers spent a whole bunch of time thinking about signal analysis and building feature detectors, et cetera, and that worked okay. But once we started to see inspiration drawn from neuroscience and applications of models like deep neural networks, we saw not just one or two step changes, but orders of magnitude improvement in our ability to do computer vision processing. So we have examples of past successes of why this might be possible. And it's not just computer vision. It's ideas of reinforcement learning. How do embodied agents and intelligent systems make decisions by learning from experiences that interact with the world? The idea of reinforcement learning is very, very dominant in AI machine learning right now. But that is another idea that came out of cognitive psychology and cognitive neuroscience in the 50s and 60s. So it's not just one example of past successes. There's many examples of past successes where our understanding of how to do engineering and build systems got better by getting a better understanding of the natural systems. Perhaps the biggest thing that is needed is the feedback from the engineered systems into a structured understanding of the natural intelligence. So what led to progress is the idea of bringing science and engineering together. The problem is that loosely coupled approach took about 40 years to yield progress on only some of the questions. So there's a lot more to understand about intelligence, both natural and artificial. And so part of the quest is a bet that if we couple these things together, as I said at the beginning of the talk, then we will move more quickly. We also believe that now is the time to make that bet because a lot of theories on both the natural and artificial intelligence side are starting to mature. So there's just a temporal aspect. We also think that MIT is the place to do it because we're relatively unique in the sense that we have a Department of Brain and Cognitive Sciences that is focusing very much on these questions of natural intelligence. It's geographically proximal to one of the homes of artificial intelligence at MIT, which is CSAIL. BCS and CSAIL are right across the street from each other. But there's not just geographic proximity. These two units happen to have intellectual proximity to each other as well. There's a lot of cross-fertilization, there's a lot of computational thinking in BCS, and there's a lot of interest in the neuroscience on the computer science side. So not only is the time right, but we think that MIT is the right place to do this, and we're unique in that regard. So how are we going to execute on this particular bet? The way that we're going to do this is we're changing the way that we do business. What we are doing is, in order to deliver on this bet, we're actually organizing research into missions in order to get to sort of advances in our understanding of intelligence in different areas. Most research on campus operates on a 2 to 5 year timeline. And this is true in almost every department in that that's sort of the natural funding cycle. That leads to, unfortunately, so part of the reason for that is that it aligns naturally with the graduate degree cycle in terms of 2-year masters and 5-year PhDs. But it also leads to a certain amount of short-term thinking. If, however, the Quest can start putting in place resources to support large-scale collaborations between multiple PIs around a domain over a long period of time, then we may actually get to some new state of the art. The other thing is that if we're really going to bring science and engineering together, we need scientists. Well, we have those. But we also need engineers, and we need professional engineers to actually take the ideas from natural intelligence and deploy them in silicon in order to actually test out the ideas. That's not an enterprise that universities typically engage in. But MIT has decided to create a team of systems engineers, and that's why my title is the Director of Systems Engineering. I happen to lead that team of professional engineers whose job it is to essentially act as a strike team to go into a lab, understand what the natural intelligence model is, build a platform that allows that model to be assessed on a regular basis in a way that most graduate students and postdocs are not set up to do. Most graduate students and postdocs are not professional software engineers. They don't build real code, by and large. There are some exceptions. And they're not committed to maintaining it. And that's part of what the Quest's mission is to actually building and maintaining these platforms that allow our ideas about intelligence, natural and artificial, to be assessed regularly and to actually measure our progress. And so by explicitly drawing and testing against experimental science and goals, we hope and expect that this will lead to rapid advances in what it is that we can do. So what are some examples of missions that we're investing in? There we go. So we launched 4 over the summer. The hope was to launch them sooner, but things happened in March of 2020 that slowed us down, as it slowed everybody down. So the 4 that we launched, the first is the development of intelligent minds. We have examples of remarkable intelligence out of very small children. And that intelligence grows unbelievably quickly over time. How do we actually replicate that? How do we understand what's happening in the child's mind? And how do we replicate that in silicon? Can we actually have systems that learn like children from very small amounts of data, from very low energy footprints, by acting in curious ways? And so on the bottom left, see here, led by Laura Schultz, Rebecca Sachs, and Josh Tenenbaum, and Pulkit Agarwal. And they are collecting data. Part of what we're doing as the systems engineering team is actually working with the Laura Schultz's lab and Rebecca Sachs's lab and Josh's lab to actually build a system that allows them to actually do experiments to study children's visual perception much more quickly and also much more systematically. So they have a system for collecting data about how children learn to steer their gaze, et cetera, and they need help in terms of actually putting those experiments on a systematic footing so that they can scale up, and that's what we're doing. Another example, and I'll talk more about this in a minute, is embodied intelligence. A lot of the successes of AI and machine learning in the last few years have largely been inside the box of a computer, maybe a computer attached to the web. So, computer vision works, I would say, best when it's processing images from your smartphone camera, still images that you've uploaded to Flickr, Picasa, or Shutterfly, or what have you. An agent that exists in the world has a very different experience. On the one hand, Those images, the images of an embodied agent, are not curated. They have all kinds of harsh optical effects, like very large, intense lighting, like here, which is creating lens flare on my glasses, which you would normally not see in an image that you would want to actually process. But embodied agents are going to have to do that. At the same time, embodied agents can act to gather more data. So there's all kinds of ways in which embodied intelligence is fundamentally different to a lot of the formulations of current AI and machine learning. It's also the case that AI machine learning assumes that the data is more or less distributed according to well-understood distribution. The kinds of photos that your phone takes doesn't change all that much. They tend to be photos of your family, photos of your vacations, et cetera. But the real world is an incredibly rapidly changing environment. And we need AI machine learning algorithms that understand that the concept that it learned yesterday might no longer be applicable today, and what to do about that. I already mentioned the fact that current AI machine learning resting on conventional computer architectures or perhaps GPUs is very, very energy inefficient. It's energy inefficient, it's slow, it's unnecessarily physically large, it's poorly aligned with what we want out of our hardware in almost every conceivable way. So this mission, led by Jesus Del Alamo and Bilge Yildiz, is they're really looking at new forms of hardware for AI machine learning. Not just new forms of computers, but new forms of the fundamental building block, the transistor. Do we have to have digital architectures, or can we do a lot better with analog architectures? What is the internal architecture that, just as the phone scales up from transistors to integrated circuit chips to operating systems, what is the right way to take an analog computer and scale that up to actually become more functional? And then the last mission that we launched is in collective intelligence, led by Tom Malone, Alexander Madry, and Jacob Andreas. And the idea here is that natural intelligence doesn't just reside in a single biological entity. Natural intelligence can often be distributed among many people. We've seen the effects of social networks, social media, for good or for ill. How do we actually understand how a social network behaves, composed of intelligent people? Another example I like to give is that buildings are incredibly complicated to build. Simple sheds, maybe a house, a single person could actually build it and understand all the necessary pieces to build it. But a skyscraper is the coming together of hundreds or thousands of people, each of whom have a different understanding of the building process, have different expertise. And I would argue that no single person actually knows every single piece of knowledge required to build a skyscraper, and yet somehow we do it. How is it that we do that? And so these folks are actually examining that particular problem as well. In the time that I have left, I do want to dig into one of these missions just a little bit deeper, and I'm going to go back to the embodied intelligence one, led by Nancy Kanwisher and Leslie Kaelbling. And I, not taking off my hat as the director of Quest Systems Engineering and putting on my hat as an individual PI, have been really excited to start working with Leslie and Nancy and some other folks to actually get at these issues of embodied intelligence. And let me just take a minute, and embodied intelligence is often thought of as robotics and autonomous vehicles. And robotics and autonomous vehicles is also changing rapidly right now. Self-driving cars are an ever-increasing presence in our lives. We see drone delivery happening with a surprising increase in number of deployed systems. The expectation is that we'll have service robots in, if not our homes, at least in our offices in relatively short order. And so what that means is that embodied intelligence is becoming an increasing reality, and that's interesting. It's worth asking the question of what's enabling current autonomy. Let's leave aside the issue of the Quest for a second. There's a few things that are enabling autonomy and embodied intelligence. One is the increasing availability of, increasing density of computation that's available in small, lightweight packages. So, the amount of computation you can carry on your cell phone is insane compared to even what it was 15 or 20 years ago. Cell phone industry has given us not just, given us great computation, but also given us a lot of the things like, high energy and power density batteries, very sophisticated electronics for estimating things around the environment, very small, lightweight, highly capable cameras. And of course, there's a lot of infrastructure like GPS that's deployed to allow a lot of these systems. But I would argue that the biggest enabler of current autonomy and the biggest enabler of embodied intelligence is actually the ability to perceive the scene. So we can recognize self-driving cars by the presence of the spinning things on top, the laser rangefinders. And laser rangefinders come in all different sizes and form factors. These ones here are too small to put on most indoor robots or drones, et cetera. But you can actually buy a lot smaller ones. This one here weighs 140 grams and is easy to put on a drone or a service robot, and people do that all the time. So this kind of high precision, highly reliable sensing has enabled a lot of autonomy recently. But things are actually improving even more. This is a drone made by a company that spun out of my lab called Skydio. And you may have seen this. It carries a ring of 12 cameras around it, and it uses those 12 cameras to actually perceive its environment. This is a video of the Skydio drone flying at a practice facility. And what you'll see is that it's actually building a three-dimensional model of the environment around it. The environment model is false colored by range, but you can pick out features of the environment like trees, et cetera, the overhanging branches, the ground plane, and the fact that the stuff right in front of it is pretty far away, so that means that it's a pretty clear path for it to fly. And the Skydio drone is not using high-precision laser rangefinders. It's just using passive imaging. It's doing a lot of fancy math on those cameras in order to do stereo, et cetera. But it's able to go relatively high speed, and it's able to go surprisingly long distances, and it's able to do increasingly sophisticated things now in terms of either following mountain bikers as they race around the park wherever they are. There's companies are buying the Skydio drones in order to actually do infrastructure inspection, power line inspection. These drones can go a lot of places, and they have an increasing understanding of their environment. So that suggests that computer vision seems to be crushing it right now. And I made the example earlier of how natural intelligence had enabled computer vision to an extent that we have things like the Skydio drone. So how come we don't have self-driving cars everywhere? Why are the self-driving cars still reliant on laser rangefinders? Why don't we have robots bringing you coffee in this room? So I think there's a couple of reasons. And I'm not going to go into all of the reasons right out of in this presentation. But let me give you a sense of a couple of reasons why we don't have ubiquitous autonomy. This is an architecture of pretty much every single embodied intelligent robot on the planet. And I'll walk you through what we're looking at here. Pretty much every single intelligent robot on the planet has a loop in terms of information flow that goes from sensors to some estimate of where the vehicle is in the world. So robots need to know where they are in order to behave usefully. So the sensor data goes into some kind of a state estimate. And your brain does this too, by the way. If you know about hippocampal place cells and entorhinal grid cells, that's exactly data from your vestibular system and your eyes, et cetera, feeding into an estimate of where you are in the world. Then that state estimate is given to a motion planner that, given some goal that it has to accomplish, the motion planner then takes information about where you are, decides a trajectory to follow in the world, gives that to a controller. Controller knows how to take a trajectory you're supposed to follow and turn that into commands to your motors. And this is how your self-driving car works. This is how your manufacturing robot works. This is how your drone works. And this works extremely well. We are able to operate robots that do this basic task very, very well. But this basic task is only good at one thing, which is getting from point A to point B in the world. If you want to do a more sophisticated mission, a more sophisticated task, like assembly, or not just driving through your environment, but actually providing a service to passengers in terms of picking up and dropping off, you also need to reason at a higher level. And pretty much every robot doing a more complicated task has this higher level reasoning block that takes the state estimate of like where you are in this room and turns it into a high level state that says, I'm in the Boston Marriott. Where exactly in the Boston Marriott? That's the purview of this thing here. And given that I'm in the Boston Marriott and it's a little after 11, my high-level plan says go to the, maybe it's still a little before 11, I'm supposed to be in a conference room. Plan says go find the conference room. That's given to a motion planner that takes that as a goal and generates a trajectory. This thing up here is what we tend to think of as real autonomy, carrying out complex multi-step tasks. This thing up here is also the thing that always breaks. If you're used to working with robots and autonomous systems, you know that this is the bane of your existence, is that this works until it doesn't. The robot, some edge case happens. You know, I was supposed to get to the conference room in the Marriott in order to give a talk, and I forgot to actually take into account the fact that I had to park my car at Stata and walk over here. The symbolic planner assumed that I could just drive straight to the Marriott, park out front, and that would be that. And of course, Boston being Boston, there's no chance I'm going to be able to park out in front of the Marriott. I have to have a more sophisticated understanding of the world here. What is it about this thing up here that breaks? Well, each of these little arrows represents a control flow. It represents not just a control flow of information through some kind of loop, but it also represents a model, an understanding of how the world works. And what I'm going to do is I'm going to circle each one of these arrows based on whether or not I can actually learn that model from data. Can I learn how to turn a motion planner into controls for my motors? Can I learn how to turn a set of sensor data into an estimate of where we are in the world? And the answer is yes. These are very, very well understood techniques. And when I say learn, I'm using a very fancy word for a very simple concept that engineers have understood for at least 100 years of how to build models, how to build models of plants to control, et cetera. I can even do it for the high-level task and autonomy up here. But notice that there are two arrows down here, which I can't color in green, because I don't actually know how to learn a symbolic representation of the Boston Marriott, the parking garage, the act of giving a talk. I don't know how to learn the relationship between those high-level concepts and the low-level stuff that my motor system is doing in order to actually get me to locomote from the parking garage to here and to understand where I am in the world. We know that the biology can do it, but we also know that the artificial systems cannot do it. We don't even know how to write it down as a problem to actually learn this. And so what we end up doing is we have engineers or graduate students, in my case, actually write snippets of software, Python or C++ or something, that basically is their best estimate of what is a reasonable symbolic state representation and what is a reasonable way of just coding our current state estimate into the statement about where I am in the world. And whenever we are hand coding things in an intelligent system, we are doomed to fail because we're just not good at it. We are much better at actually allowing the real world to express itself through data and fit those models. So I don't, unfortunately, have an answer for this, but I am going to say that reliable long-duration autonomy will require a true understanding of the environment, and true understanding will require getting the representations right. And let me just, with the 3 minutes I have left, give you one super quick example. I said that computer vision is doing a really good job right now. Computer vision is actually doing a really good job at one kind of thing, which is recognizing objects. So I can give the street scene to any of a number of commodity computer vision object recognition systems and ask it to label the things that it knows about. And so it recognized the cars, it recognized the flags, et cetera. But it missed a bunch of stuff. I use the word stuff advisedly. The things that computer vision is good at recognizing are the things where we can put a neat box around them. These are objects. These are things. Computer vision is much less good at recognizing the spatially extended things, like the trees waving in the wind, or even better, the road surface. It is crazy for me to put a nice, tidy bounding box around the road surface, but if I'm an autonomous agent existing in the world, knowing where the road surface is really, really important. That's a great signal. And furthermore, we also know that this dichotomy between things and stuff exists in the brain. The ventral stream appears to be aligned with recognizing objects in the world, the things. But the dorsal stream runs in parallel to the ventral stream, and it recognizes spatially extended stuff, and it recognizes context, and it's what's called vision for action. And these are separated in parallel. And when I learned that these were separated in parallel from Nancy Canwisher, it completely blew my mind, because as a roboticist, I would never do these things in parallel. I would do them sequentially, because there's tremendous utility in actually having the vision for perception stream actually feed the dorsal stream. And that's the way a lot of robots do that. But that's not the way the biology does it. I have no idea why. And one of the things that we did in my lab, so this is a quick video of a drone flying. This is a place where we fly. It's actually an abandoned state hospital in Medfield, about 45 minutes from here. What the drone is doing is it's actually building a semantic understanding of all parts of the scene. It's extracting the stuff to the extent possible. It's getting the road surface, the grass, the sky, et cetera. And then it's retracting that representation into a trajectory that it can follow in the environment. There's a bunch of math that's involved in how you actually do that retraction, et cetera. But when we were trying to reason about the world in terms of distinct geometry, the way that most robots do, and a detailed map of the world, we couldn't do it fast enough, and so we were limited to 3 to 4 meters per second in terms of flight. Once we started actually building a model of visual perception for action and actually understanding the world around us in terms of semantic concepts, all of a sudden we could fly 9 meters per second. So this is just one example of how the natural intelligence, I don't want to overstate it. It's not like we went to Nancy Canwisher and said, tell us how the vision system works. We built it, put it in the quad, and all of a sudden we could fly 9 meters per second. But it was interesting that the system that we stumbled on here actually has a parallel to how the natural intelligence system works. So my claim is that computer vision is crushing it only in narrow ways right now. And it's not actually up to the task yet. We have a lot more work to do. What about planning and decision making? I only have 8 seconds left, so unfortunately, I'm not going to get to the statement about planning. So if we can just skip to the last slide, if you don't mind, the gentleman at the back. I'm just going to end here and say that the quest for intelligence, I'm super excited to be part of this organization now. I'm really happy to be leading a team of engineers whose job it is to take ideas from natural intelligence and the biology and really test it out in the real world. And these are the 4 missions that we've got started. If you're interested in getting involved with these missions, please reach out. Or if you have ideas for missions, other missions that could parallel, like some that are obviously missing from here are natural language and how do people communicate. That could maybe fit inside collective intelligence, but probably not. It probably deserves to be its own mission. Another one that we're looking very hard at is the intelligence of really big systems. Humans are surprisingly good at controlling big systems like the energy grid. I made transportation systems. How do we do that? That to me seems to be a fundamentally different enterprise than collective intelligence. And so we're talking to a lot of the people in civil and mechanical engineering about how do we actually work with them to bring AI, to actually get an intelligent understanding of how those systems work and couple that with AI. So I think there's tremendous opportunity there. Anyway, thank you very much for your attention. I see questions filling up on the board here, so I will conclude and say thank you very much and happy to start with questions. All right, so the first question here is why not start, oh good, you can see it. Why not start with models of simpler animals such as insects, which would be easier to understand or still vastly superior to current generation robots? Interesting question. We certainly do start with simple animals. I think that there's value at starting at multiple levels of the sort of the complexity pyramid, for lack of a better word. That there are people examining at a low level. I don't know if we have anybody studying insects, but certainly invertebrates, et cetera. And we also are examining how mice behave. Jim DiCarlo, the director of the Quest, has a long and rich research program in examining monkeys, et cetera. So I gave the example of robots because that's sort of like my own passion. I actually would disagree that insects are necessarily vastly superior to current generation robots. There's lots of things our robots can do that insects can't do. At the same time, there are definitely things that insects can do that our robots can't do, no argument. So I think it's not one is better than the other, but they have different abilities, and we'd like to understand the abilities. I also think that the part of the reason why I think there's value in at least having some research higher up the complexity pyramid is because I think this idea of structure and modularity is really, really important. And insect reasoning does not appear to have the same level of structure and modularity. The kind of, for instance, memory that an insect exhibits is very, very remedial. The ability for an insect to modify its environment by itself is very, very remedial. And we know that the ability to interact with the environment is key to higher levels of intelligence. So I don't think if I gave the impression that we were just focusing on robots and we weren't looking at simpler systems as well, then I didn't convey the message as clearly as I hoped I did. But at the same time, I think that we have enough excitement on campus that we want to start at sort of multiple levels and have the levels talking to each other. Anyway, thanks for the question. All right, how much does your research consider biomimicry, such as bee behavior in natural intelligence applications? That's a great question. Does the Quest consider biomimicry? I think the answer is yes, to a certain extent, but I don't think it's an area that we have a lot of investment yet. And I think that's an area where we absolutely would want to invest sort of time and attention. My own research has looked at Not necessarily biomimicry of this kind. Certainly, we've looked at being able to learn from humans and learning from demonstration. That is another idea that has come out of natural intelligence and cognitive psychology, is like, how can intelligent systems learn from demonstrations? And there's ways to make it easy and there's ways to make it hard. So I have a kind of unsatisfactory answer to this question, which is that I don't think the Quest is invested in this, but it's something we're looking at hard. And we're still trying to figure out what is the actual sort of mission that will be involved here. And then my own personal research, I think that learning from demonstration is super useful, but it's not the same kind of biomimicry that's described in this question. So, are there any examples of systems that can improve themselves through code instead of simply refining an ML optimization algorithm? The answer is yes. I'm not sure that I completely understand the difference between code versus ML optimization. I think ML optimization in this case refers to, like, parameter tuning. So can you, given a structured representation, such as a neural network, can you improve the parameters to perform? And can you, are there examples where you can actually improve through code improvement? So if I understood that question correctly, the answer is yes, absolutely. I think that one thing that has emerged, one idea that has emerged in the last 3 or 4 years is that there's the improvement process, and then there's the language you use to express the concept you're trying to capture. Computer programs are a way of expressing concepts. Neural networks and functions are another way of expressing concepts. The thing that has worked best for neural networks is the idea of gradient descent and auto-differentiation. So you can basically, like, twiddle things, see if things got better or worse, and if they got better, you keep twiddling them in that direction. That's basically what gradient descent is. And that has worked extremely well for neural networks, but people have realized, like, you don't have to just do that for neural networks. You can actually use gradient descent inside structured computer software. And there's multiple examples of this in the programming community, programming languages community, even in the robotics community. You can take a standard robotics control architecture and actually backprop through it or do gradient descent and actually get improvements, which is not something people ever thought was a good idea, but actually turns out to be a great idea. What I do think is right now the biggest open challenge is that code and programming languages and software is a very structured and modular way of expressing ideas, so that I can take a library and I can reuse it in lots of different places, and so long as I've used it in the correct way according to the specification, I know it's going to work. And software engineering in general has really profited from this idea of modularity and composability. Machine learning models right now appear to have no language of composability. So you can't take a neural network or 2 neural networks and stick them together and make any sense of the output. You have to retrain. The neural networks are composable in the sense that it is sensible to put them together, but the output won't make any sense, and you've got to sort of retrain the entire model, and that's really frustrating. Logic, really, really old-fashioned AI, is composable. There are well-defined rules for putting together logical statements in a way that preserves the semantics. You don't break things. And so I think that people are starting to turn their attention to how do we actually get the composable power of logic and computer programs, but at the same time we get the expressivity of machine learned models. And there is work going on there. A lot of the people that I referred to already are looking at exactly this question, but it's very much an open question, and we're still trying to figure out how to make it work. But that was a great question. How can companies be involved in the Quest? The short answer is that our managing director, Eric Vogan, who unfortunately is on vacation this week, but he would be a person to reach out to. So if you'd like to contact us, please, so quest.mit.edu is our website, and there is contact information. You can send email to me, or you can find Eric Vogan's contact information there as well. And we'd love to have you involved. We have a rich and robust corporate partners program. That I think Carl helped us set up too. So thanks to ILP for helping us launch that. Is that the final question? All right, very good. Thank you very much. Enjoy the rest of your day.